Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And this is the DADM 3 which is data analysis and decision making 3 course under NPTEL MOOC series, and this total course duration as you know is for 12 weeks, which when counted in the number of contact hours is 30, and when broken down into number of lectures is a 60 in number, considering each lecture is for half an hour. And as you can see from the slide, this is the 57th lecture, which is the second lecture in the 12th week, and after each week lectures, which is 5 in number of half an hour each, you take the assignments, and then after the completion of this whole course, that means after you have taken 12 assignments, you will be appearing for the final examination. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we were considering the concept of reliability based optimization, and I was mentioning time and again that you have the x plane in which the decision variables, the parameters which are stochastic or the parameters which are deterministic, all are being calculated and measured. And in order to basically consider the concept of reliability based optimization or reliability analysis, what you do is that you use Rosenblatt transformation, considering the fact, if you remember, I said that the main concept being the CDF values are between 0 and 1 for the corresponding distribution, which when converted into the normalized standard normalized independent random variables use, you convert each of them of the x's into u1, u2 till un, and also the probabilistic parameters, and then basically optimize that using the PMA or the RIA method, which is actually where you minimize the distance of u subject to the constraint that g prime is equal to 0, or considering trying to basically consider minimize the g prime function or g function based on the fact that the norm of u is equal to beta. Beta is basically the level of reliability. So, when we are considering the level of reliability, considering both of them are normal and have the same variance, they would be circles, and the radius of the circle in the u space would be moving in such a way that it will increase or decrease depending on the level of reliability, and the loci of the reliability point, which is the best optimum solution based on the level of reliability, will have a loci. Now, when you come to the u space, as I mentioned for the RIA or the PMA approach, your main concern is to find out the most probable point. Most probable point is basically the best point depending on the level of reliability, which will give you that optimum solution in the reliability space, which when back transformed into the x space will give you the next stage of the iteration. And we also mentioned one important thing, the point from where you will start the iteration in the x space, because in the SORA method it is sequential optimization, it is decoupled loop. You do the optimization, take the first step result, and then go into the u space, do the reliability analysis, then map back into the x space and continue doing this till the level of level of accuracy is reached. Now, remember one thing, in case if it is a non-normal distribution, you will use the same concept. So, there is no change, only the fact that I was mentioning time and again, that in the normal distribution case it is very easy to understand that how the calculations can be done considering the univariate case or the multivariate case. And I did mention the diagrams which I drew will be repeated time and again in order to make things clear. So, after the 57th lecture, most probably in the end of 58th or 59th and 60th, we will consider the robust optimization concept also. So, generally the reliability optimization flow chart works like this. So, in the first step, when k is 1, so k is the number of iterations you are doing. When k is 1, you take x MPP, x MPP is the most probable point in the x space, that is equal to the mu suffix x naught. Naught is the first iteration. So, you will take the mean value, and similarly so I will just mark it in order to make it clear. So, x MPP is the mu suffix x naught, which is the first iteration, first value, and the first value for PMPP, which is the most probable point for the probabilistic parameters, is mu suffix p. So, also they are the mean values, and obviously with the not sign, which basically means the first iteration. So, and you will basically be doing the iteration time and again. So, you will start with d naught. D naught, remember, is the deterministic parameters which would not be changing. So, d naught mu p for the parameter values which are stochastic or non-deterministic, and mu x are for the decision variables which are non-deterministic. So, you will basically reformulate the probabilistic constraints, so which are given, and based on the equivalent deterministic constraint. So, you will just remove the probabilistic constraint, have the deterministic constraint, solve the problem. So, here they are, but remember one thing, when you are replacing them, you will be replacing them by the corresponding mean values of x and mean values of p, which is the vectors. And this S, when you start off the iteration, is basically the amount of movement from the mean value at each and every step. So, the moment the rate of change, I would not use the word rate of change, the change of the functional value is now no more relevant. That means, f x minus f x the previous value. So, f x t minus f x t minus 1, if that is less than equal to epsilon, a very small value, then you will obviously terminate your iteration values. So, the constraints would be mu x minus s, s is the increment. So, which is 0 in the first step, because that is the decision variable which you are going to change to find out what is the optimum value, and PMPP is basically the most probable point for p. So, this greater than 0, less than 0 are immaterial, they can be with respect to greater than b 1, less than b 1, whatever, and you do it do the optimization. Once you do the optimization, the deterministic optimization problem is like this: you minimize or maximize whatever the problem is, subject to the constraints of j number of them, where you replace, again I am repeating, replace the x with the mean values, p with their mean values, which is the PMPP, and do the optimization. Get the results. Once the results are obtained, you so here p's are not changing, only mu x or the x values are changing. When the mu x's are changed, you basically put them in the reliability space, or the reliability analysis is coming, you do the inverse reliability assessment, find out the next stage of XMPP. So, XMPP initially was mu naught suffix x. In the next stage, when you do the reverse reliability analysis, do the reliability analysis using the PMA or the RIA approach, map it back to x space, it will be, say for example, x1 MPP, that means x1 is the first iteration stage. Then you basically find out whether the objective function converges or not based on some set boundary values. If they do not, then again you do the optimization in the x space, find out the values of x in the second iteration, map it back to the u space, do the reliability analysis using the PMA or the RIA approach, find out the new MPP points, map it back to the x space, find out x2, and continue doing this till you basically reach the optimum solution, or the iterative value is basically reaches an optimum value. In the sense, the difference basically becomes as small as possible. So, you do the inverse reliability assessment, find out x MPP and PMPP. You ask the question whether the objective convergence has been achieved, where the constraints are feasible. Obviously, when you are doing the objective analysis to find out the convergence, you will find out whether all the constraints are applicable or are they feasible. If this is achieved, you stop the process. If not, you basically shift that s amount, the delta amount by which each x values would be changing, by the value of mu x, which is the initial value minus the MPP points. Then you will basically increment k by k plus 1 into the next stage, and then repeat the process till you basically achieve the optimality conditions. Not condition, not mathematically, but you basically reach the optimum values. So, generally the reliability stochastic optimization in a very general sense, I have discussed that, but I will still repeat it, is given by optimize of a set of functions f1, f2, f3, and here f1, f2, f3 are all different type of functions which can be linear as well as non-linear. So, that means in the case we have the multi objective problem, and x d p are the decision variables, d is the deterministic parameters, p is the probabilistic parameters, and the constraints are like this. GJs which are probabilistic, which we will consider later on, and we have already done that in the previous reliability analysis concept. Other case for the reliability analysis problem, we considered BJs was 0. So, it need not be 0, and there are other sets of k number of constraints, small k is equal to 1 to capital K, where the constraints can be considered as deterministic. So, we are trying to basically segregate into deterministic and non-deterministic part. So, if all of them are deterministic, so it is a deterministic problem, no stochasticity is there, no probability concepts are there, no reliability, no robustness, and if all of them are stochastic, so obviously you have to consider their corresponding MPP points for each and every constraints accordingly. And x is in the n dimension, d is in the m dimension, and p is in the l dimension, depending on number of decision variables, deterministic parameters and probabilistic parameters which are there. So, I is equal to 1 to n, depending on the number of such objective functions which we have. So, here f x dp's are linear or non-linear objective function, depending on how the problem formulation is done. And you see the red colors, they actually signify which of them are stochastic. GJs are the constraints where BJ are deterministic. We are not going to consider the right hand side as the non-deterministic. So, they will be fixed, only the concept of stochasticity would be coming in the parameter values P, which are external to the system, and the decision variables based on which you are going to take the decision. And HKs are the constraints where CKs are probabilistic. So, the right hand side, here we have basically divided the right hand side into two different sets. Sets means two different type of constraints, one of them which are deterministic, another sets are non-deterministic. X is the decision variable or the control variable which are probabilistic. D's are the deterministic control variables or decision variables, and P's are the probabilistic exogenous parameters which basically dictate how the overall effect is there on the constraints. BJs are the input which are deterministic parameters, and CKs are the input which are probabilistic parameters. So, here x, d, p, b and c may be continuous, discrete, integer, binary, positive, depending on how the problem formulation has been done, depending on the scope of the problem, and if it is a multi-objective problem, obviously f I, which is the objective function, would be more than 1. So, it can be, as you have seen in the case of quadratic programming, there were two parts, one was the quadratic part, one was the linear part. Quadratic was x, qx, x are all vectors and q's is a basically matrix, and the linear part is c into x, where c and x are both vectors. How you denote them, whether a column vector or a row vector, will depend on how the problem formulation has been done. The probabilistic optimization is an optimization technique where we model the optimization problems with data uncertainty. We need to find a solution that is robust and reliable to the data perturbations or the data fluctuations or data uncertainty which is there. We need to find a solution that does not violate the critical constraints. So, it will be feasible, and based on the feasibility we will get the optimum solution based on the conditions. We need to find the global optimum of the objective function value, considering that uncertainty is in both the model parameters as well as the variables. Model parameters are the p and the variables are the x's. The available classical methodologies is sensitive analysis, which we have considered though briefly in the linear programming. It can be done for the nonlinear part also, and one is the stochastic programming or reliability programming or robust programming, which we are discussing in quite details. The probabilistic nature of the optimization comes from two different sources, which are set of the variables x and p and the input parameters, which is ck, which is on the right hand side, because the bj's are all deterministic. So, there are three different sources. One is the decision variables which you want to take, one is the external set of parameters p, and one is the constraints, the right hand side of the constraints. Few of them So, the set k of them are non-deterministic because C1 to Ck are probabilistic in nature. They will have a distribution per se. So, the generic probabilistic optimization would be optimize. So, here it is the same slide which we have considered, but with the change that the red colors have been marked for the case which are now no more deterministic, but they are probabilistic. So, you optimize the functional form f i's which is a function of x dp, and x and p are probabilistic because x is the decision variable, p is the parameters which are external and which are probabilistic. The constraints have been divided into two parts. In one case it is this GJs where the right hand side is deterministic. So, they remain as deterministic constraints, and in the case if it is right hand side is CKs which are probabilistic, we will basically model that as a probabilistic constraint. Now, here if you remember I have been talking about alpha, here we have just replaced alpha by beta k's. So, you have the probability of HK which is a function of x dp is greater than or equal to or less than equal to Ck, and that has a probability of Bk's. Bk's means they will be different values of betas, and that will depend on the decision maker who is going to make the decision and do the optimization. Again x is in the n dimension, d is m dimension, and p is l dimension. Now, this diagram I have already discussed, but I will still go through it. So, here in the 2 dimension problem you have x1 along the y axis, x2 along the x axis, and the actual boundary for the deterministic constraint is the bold green line. I do not want to draw too much here because or else it will get cluttered, but if the camera is focused on this diagram I can continue talking. So, rather than focusing on me, if it is focused on this this slide, it will basically clear all the doubts. So, the green bold lines are the constraints which are deterministic, and the red point which is there, which I will not highlight, again I will just hover the electronic pen. So, this is the deterministic optimum solution which can be solved using any of the deterministic tools. Now, what we consider is that the constraints can be perturbed as per the sensitivity analysis, they can move like the right hand side changing plus or minus 1. So, the constraints for the green line constraints basically fluctuate with some probability. So, the small dotted one and the bold dot and the large dotted ones, these are the range based on which the values you want to find out that how the constraint basically can fluctuate. And the feasible region which is inside, it will shrink, the total number of such feasible points or feasible space will shrink depending on how high or how low your reliability is. And we consider that x1 and x2 are normal. In case if they are normal, then you have a circle. In case if it is 3 dimension, you will have a sphere or like a football. In case if they are normal, but one variance is higher than the other, we will have a sort of baseball shaped overall ellipsoid, which will give us the feasible the optimum point, the center of gravity of that will give the optimum point based on the level of reliability. In case if they are not normal, then trying to find out the optimum space inside the feasible region would be difficult. So, there are different areas which have been shown depending on the reliability. So, the blue one, bold one is for the case when it is along the boundary, and it is no more normal as I said, and the small dotted ones and the large dotted ones or the last hashed ones are the level of the reliability space, and the center of gravity is the optimum solution depending on the level of reliability which you have. So, outside you have the feasible infeasible region, and this dotted one which goes up is the loci of the reliable robust solution. So, there are different reliable robust feasible space which are given, and remember one thing, these red distributions which are given are the marginal distributions of x1 and x2 correspondingly, and obviously the joint distribution would be important for us. So, this is the fact, if you have in the rightmost panel is the one where we consider both the variances of x1 and x2 to be equal, hence the common area or the feasible region are circles, and these circles would basically move inside the feasible region depending on the level of reliability being increasing or decreasing. In case if you have The second panel is in case if we have the variance of x 2 is large. So, it will be a baseball or an ellipse or an ellipsoid kept where the major axis is horizontal. In the case if the variance of x 1 is more, in the initial case it was x 2 was more, in the first panel if the variance of x 1 is more, then it will be an ellipse or an ellipsoid where the vertical axis is the major axis. And you can find out how the optimum solutions can be obtained. So, I have do it, but these I thought were nice diagrams which could be discussed, and I have just made it in order to explain you in much details. So, we need to find out the optimum value of the decision variables under the set of constraints, which is the probability of GJ's or H whatever it is where we define is greater than equal to beta, and plotting the probabilities with GJ's provide us with the probability that is as it depicts the instances when the area under the curve is greater or less than equal to beta. If you remember the graph which we said on the right hand side, so alpha area was there. So, you want to find out the probability that it is equal to of BJ's. So, BJ's are the values based on which we will basically find out what is true or which is feasible. So, you can find out greater than equal to less than equal to and less than equal to beta j, which holds true, and we basically find the solution. Given a predefined performance level, one is interested to find the probability or reliability greater than or less than the predefined performance. So, the idea of inverse probability would be utilized, and it is formulated by trying to find out the. So, if you remember that what we did, if you have capital F of x and is equal to the value of alpha, you find out the inverse probability and find out the small x values or the small z values. So, this inverse probability will be utilized to find out the values of depending on the values of beta, you want to find out the values of x, which is the decision variables, and obviously they would be utilized in order to find out the x MPP points and similarly do the reliability analysis. So, this would be satisfied when G to beta is basically beta percentile performance would be given by the difference of the functional form of the constraint GJ's minus BJ's. So, we will consider few very simple models and I discuss about that. So, in the first model it is a multi objective where F1, F2, F3, F4 are given. The 1, 2, 3, 4 values are corresponding to the case where the first value for I is equal to 1 is the expected value, hence you are trying to maximize RP. Next I is equal to 2 is basically you want to find out the minimum variance and it is minimization of the variance. The third one is basically you want to find out the maximum value of skewness. So, it is given by maximization of value of S with a suffix p is basically for the portfolio, and the last one is the minimization of the kurtosis. So, we basically have two maximization problem and two minimization problem, and I want to basically find out the multi objective the solutions for this. What are the constraints? In the simple case, the constraints are given like this: 2 are deterministic and 4 are probabilistic. What are the deterministic part? Deterministic part is the initial wealth, which is the number of stocks multiplied by their corresponding prices is equal to V naught, which is the money which I have. Second one is that the prices of each and every stock would be increasing and decreasing, we do not know, but in overall sense we should find out that the sum of the multiplication values of the stock numbers multiplied by the corresponding prices, if they are added up, it would always be greater than V naught, or else it does not suffice that why we are investing. If we cannot increase our wealth, obviously it does not suffice. The next 4 constraints are the probabilistic one, which are like this, and with a level of reliability or beta values given by beta 1 to beta 4 depending on the level how we perceive the level of risk for that to be. Risk means the level of reliability to be. The first constraint is that the portfolio returns, considering that you are taking a sample, should be greater than the RP value which you want to basically maximize. Maximize means if you are considering from your side, you will try to push it more onto the right, returns being higher. So, hence it goes away from 0 on the right hand side, and that has a probability of beta 1. The second one is basically the overall combination of the portfolio variance, which is double summation Wi Wj into multiplied by sigma ij is less than or equal to sigma square p, which is where sigma square p is the set variance which you want to minimize. That means push it on to the left, more away from the 0, but on the left hand side. The probability is beta 2. Similarly, the probability is beta 3 for the third constraint, which gives us some idea that what should be the skewness values of the portfolio, so that is greater than SP, or which we want to maximize. So, push it on more onto the right, away from 0 to the right hand side. The fourth constraint has a probability of beta value as beta 4. So, beta 1, beta 2, beta 3, beta 4 are, as I mentioned, they are dependent on the decision maker, they can be equal also. Hence, coming back again to the fourth constraint, it is the kurtosis value of the overall portfolio should be less than equal to Kp. Kp is set value which we have taken in our optimization problem, and you want to minimize it, like push it onto the left, more away from the 0. And one should remember the constraints have been formulated. Other sets are that Ni values, which is the number of stocks which I want to buy, is between a minimum and maximum value for each and every stock. We will also consider the weights which can be found out using the Ni values is also bounded between 0 and 1, or between the values of minimum and maximum. So, it can be depend how you have able to formulate the problem, and the weights Wi's are given by, for each stock I am basically finding out its total investment which you are doing in that particular stock, which is the multiplied value of the number of assets multiplied by stock prices divided by the total amount of money which I have in my pocket. Now, remember, in the initial case, a summation of Ni into Si should be exactly equal to V naught, which you have already done as one of the constraints. So, the weights can be found out accordingly. That means, total number of investment which I have done for that particular stock divided by the total investment I am doing in totality. The second problem is also a multi-objective problem, but now we have two objectives. So, f I is equal to 1 to 2, and without repetition I will just go through it. So, the first constraint remains the same, which is the fact that the sum of your portfolios, that means the Ni into Si, is exactly to V naught, the money which you have in your pocket. The second one is where the initial amount of money which you had in your pocket should increase with an interest rate of Ri, the returns was for each and every stock which you have, and that the overall summation of the number of stocks which you want to buy multiplied by their corresponding increase in the prices should be greater than equal to V naught. The second and third are corresponding to the first moment and the second moment, which is basically related to the return of the portfolio and the variance of the portfolio and the beta values of beta 1 and beta 2. And again, Wi is exactly equal to the same, where I invest, if I invest total amount I have in my pocket is V naught. So, each investment which I do in each and every stock, that value divided by V naught will give me Wi, and obviously the sum of Wi should be 1, which I have not written here, because that can be it definitely has to be considered. The Ni values is basically bounded between minimum and maximum, which is the number of stocks which I can invest, and Wi is obviously is bounded between minimum and maximum, where minimum has to be 0, maximum need not be 1, because based on the case this maximum value need not be 1, which I am saying that in that case the negative values should also be true for Wi if short selling is there, which I am not going to discuss now. Model 3 is basically considering the minimization of the variance subject to the concept that we are trying to basically find out the returns greater than a value of D with the probability of beta 1. Similarly, we will consider the concept of the risk, whether conditional value at risk or value at risk can be considered, and the model can be done accordingly. Again, we will consider the minimization is there for all the values of Wi's, the Wi values are between minimum and maximum, and the sum of the weights is equal to 1. So, with this this I will end the 37th lecture. So, the 38th, 39th and this 57th lecture. So, with the 58th, 59th and 60th I will basically complete the course, but obviously I will lay stress on the robust part. And in one of the last lectures I will extend it with for about 15-20 minutes. I will wrap up few important things which I think would be important for you, how you analyze the optimization problem. So, as I end the lecture, I have already thanked you all of you, but I want to wish all of you a very happy Durga Puja, Dashera, Diwali. So, obviously you will be hearing all these lectures in the due course of time, maybe during the just before the Dussehra, but I want to wish all of you a very prosperous and a nice festival, and I am sure with God's blessing all of you will do very well in life. And as I said, I will also wrap up, which I am just repeating it, I will wrap up few extra minutes in the last lecture to basically highlight the important points which are there for this course. Have a nice day and thank you very much.